Hello and welcome back to Counting Rocks, an Introduction to Combinatorics at CSU. Today we're going to be talking about graph optimization and a few problems involving optimizing some choices of networks or tours in graphs given some constraints. To set up, let's consider weighted graphs. A weighted graph is a graph in which each edge also is assigned a real number weight. So for instance, this edge is labeled 0.8, that's the weight of that edge. Now, weights can mean a number of different things depending on what your circumstances are. For instance, maybe these are cities with distances between these points on the map. So for instance, 0.8 might be 0.8 miles from this point to that point, or 0.8 of some other unit, or it could be resistance in wires or some other type of number telling us how much it costs to travel over that edge. Now, one thing we might want to do given a graph with weighted edges is find a spanning tree, and ideally a spanning tree with minimal cost. Here's a common application. Say you have a bunch of cities separated by distances on a map, and you want to connect them all with a minimal amount of wire to make a network so that every city is connected to every other city within the yellow network. And also it has the minimal cost, so you don't want your cost of how much wire you need to connect these two cities to be more than necessary. So for instance, we would use this 2.2 edge rather than using this 3.5 edge to connect this vertex to the rest of them. And so the question is, how can we find a minimal spanning tree for the graph? A spanning tree is a tree, meaning a connected subgraph with a minimal number of edges, that spans the graph in the sense of every single vertex is part of that tree. So we want a spanning tree with the minimum total sum of the weights of the edges here. So there's an algorithm to do this. It's called Kruskal's algorithm, and it's basically just the greedy algorithm. Greedy algorithm means we always do the optimal choice at every step, and that's going to make the total optimal choice in the end. So what you can do is just pick a minimal weight edge. If there are two edges of weight 0.8, you can pick any one of them, and you pick that to be in your spanning tree. And then at every step, you always take a minimal weight edge that doesn't form a cycle with the edges that you already picked. So for instance, the next smallest weight edge is a 1, and that doesn't form a cycle with this yellow edge, so we can pick it. And then we can certainly add this 1.4 as well. Now, we can't add this 2 because that would create a cycle. We don't need that 2. These two vertices are already connected to each other via this one. And so instead, we add the 2.2 rather than the 3.5 because this one is smaller, and we found the minimal spanning tree. So in the textbook, there's an explanation of why Kruskal's algorithm always does give you a minimal spanning tree, but for now, we're just going to use it. So here's a very famous optimization problem in graph theory, is the traveling salesman problem, and it involves taking a certain walk that visits every vertex and then comes back to where you started. This is called a tour. A tour is a walk that visits every vertex. You can repeat vertices or edges, and you start and end at the same vertex. Here's an example of a tour. Let's walk from A, starting here, to B, to C, to D, to E, to F, back to E, and back to A. So I've repeated this edge, I've repeated E, and that's okay. You can repeat vertices and repeat edges. It doesn't have to be a Hamiltonian cycle, but it does have to hit every vertex. So say you're a traveling salesperson trying to go to every city in this graph, and you want to know an optimal way of doing it. We can say some things about it by going back to the notion of weighted graphs. Let's put in what might be a distance between cities, a weight on each of these edges, and we want to know the minimal cost tour. How can we make a tour that has the smallest possible cost? While the traveling salesman problem is very hard in general, we can say some things about it for very special types of graphs. One of the special types of graphs we can deal a little better with is a graph satisfying the triangle inequality, and that means that for any triangle in G with weights A, B, and C, like this triangle at the top here, the sum of the weights on any two sides is greater than or equal to the third weight. So you see that this triangle satisfies the triangle inequality. So in general, a graph that satisfies the triangle inequality is like a graph that can be embedded in the plane, where the edge weights are distances because distances do satisfy the triangle inequality in the plane. So here's how we can use spanning trees, our Kruskal's algorithm for spanning trees, to find a minimal tour, or at least a small enough tour. First, let's find the minimal spanning tree, and this is a bit of a different graph than we had before. So you notice we also need this little 1.2 edge from C to F, because I didn't have the vertex F before. And when we find the minimal spanning tree with Kruskal's algorithm, we have a 0.8 edge, a 1 edge, a 1.2, a 1.4, and a 2.2, and those add up to 6.6. So that's our minimal spanning tree. We know that by the greedy algorithm. Once you have a minimal spanning tree, you can use it to make a tour by tracing around the tree, sort of hugging the tree, and going around each edge, just looping around it this way, as I'm following these green arrows. You are also allowed to skip a vertex that you've already been to if you can directly go there. So for instance, if we start at B here, okay, I'm tracing around the tree, following these green arrows, down to E, back up to A, and now at this point I do have an option of traversing the edge from A to B instead of from A to C to B, and that's going to be shorter because of the triangle inequality, because 0.8 plus 1.4 has to be bigger than 2. So this is our tree shortcut algorithm. We trace around the tree, but we take a shortcut whenever there's a triangle that allows us to do that. If we do that in this case, we see we have 0.8 plus 1 because we did this edge twice, plus 1.2 twice, and 1.4, and then we do the 2.2 twice, and finally we cut back on our shortcut with a 2, and we get 13. So let's think about what this does. Hugging the tree traces it exactly twice, and that's without any shortcuts. So that means with taking shortcuts, we get, with the tree shortcut algorithm, that gives us a tour that's at most twice the cost of the minimal spanning tree. Also, you can't get any less than the cost of the minimal spanning tree, because let's think about it. If we have a tour and we remove some edges that make it a cycle, then we can remove enough edges to make it a spanning tree, and so we have to be at least the cost of a minimal spanning tree. So somehow we're at most twice the cost of the tree and also at least 1 times the cost of the tree. And so that gives us a bound on where the optimal solution for the traveling salesperson problem lies. Indeed, here 13 was our answer for our tour, and that's less than 2 times 6.6, which was the cost of the minimal spanning tree. As a corollary, the tree shortcut algorithm yields at most twice the cost of a minimal tour, because a minimal tour can't be any less cost than the cost of the minimal spanning tree. So now you try. Can you find the minimal tour in this graph? And how much lower cost than 13 can you find? And that's all for today, and I'll see you next time.